Hi, I'm Wang and very thankful to have this opportunity to share my recent research about the thermoelectricity. This work was carried out with Professor Tsing Hua. I was in Professor Tsing's group, and now I'm teaching in Te-Hsien University. Yeah, the Te-Hsien is very beautiful place, and welcome you come to Te-Hsien and visit Te-Hsien University. What is the thermoelectricity? The thermoelectricity is about the is a science and technology about the conversion between the electrical energy and the thermal energy. The most important phenomenon of the thermoelectricity is the feedback effect, which tells us we can use a temperature difference to generate electricity. The reverse effect is the Peltier effect, which tells us we can use the electrical power to create a temperature difference. So there are some applications. By using the feedback effect, we can recycle the waste heat and generate the electricity. For example, here the gas company Zhongyu and the steel making company Zhonggang, they have a lot of waste heat. So they use the thermoelectric module to generate electricity. And this person is my colleague in Nat'l University, Professor Zhu. He cooperates with the local hot spring industry and recycle the waste heat from the hot spring and generate electricity. Not only for something big, it can be used in something small. It's a smartwatch. You don't have to change the battery or charge the battery. The thermoelectric device in it will power the watch by using your body heat. The thermoelectric device can be also used as a cooler. Unlike the traditional cooler, which need a quite big mechanical compressor, which could cause noise and vibration, the thermoelectric device is a solid-state device, so it can be very small, silent, and stable. So it can be used in our household appliance, something like this ice cream maker. And this is the thermoelectric wine cooler. The vibration of the traditional refrigerator could deteriorate the flavor of the wine. So the thermoelectric wine cooler can solve this problem. To evaluate how good a thermoelectric material would be, we use the figure of merit ZT, which is proportional to the electrical conductivity, the square of the spec coefficient, and inversely proportional to the thermal conductivity, which contains the electric part and the lattice part. We want high electrical conductivity so that we can reduce draw heat. We want large magnitude of spec coefficient so that for a given temperature difference, we can get a large voltage. We want low thermal conductivity so that we can more easily to build a temperature difference. This is the power generating efficiency as a function of temperature difference. For different ZT, here we can see the higher ZT, the higher efficiency. And the red dots are those for traditional and the commercial power generating technologies. Here we can see all the red dots are above the line of ZT equal to 4. However, to date, we don't have any material that is widely accepted to have ZT larger than 4 to complete these technologies. In fact, we don't have ZT larger than 3. Why high ZT is so difficult to achieve? The fundamental reason is these thermoelectric parameters, the electrical conductivity, the feedback coefficient, the electronic and the lattice thermal conductivity are not independent. They are related to each other. So there are some trade-off relations make high ZT difficult to achieve. So let's see the first trade relation, the Whitman law. The Whitman law tells us the electrical conductivity is proportional to the electronic thermal conductivity. So generally, we cannot get a high electrical conductivity and a low electronic thermal conductivity at the same time. For metals, the electronic thermal conductivity is much larger than the lattice thermal conductivity. So the ZT is almost only determined by the magnitude of feedback coefficient, which is small for metals. So generally, metals are not good thermoelectric materials. Generally, good thermoelectric materials are semiconductors. This is a typical thermoelectric behaviors of the thermoelectric parameters as function of carrier concentration. Here we can see there is a trade-off between the electrical conductivity and the seedback coefficient. With increasing carrier concentration, the electrical conductivity increases, but the magnitude of seedback coefficient decreases. So generally, we cannot get a high electrical conductivity and a large magnitude of seedback coefficient at the same time. For semiconductors, the VT can be significantly improved by decreasing the reducing the lattice thermal conductivity. However, in most cases, the lattice thermal conductivity is reduced by introducing defect, which could also deteriorate the electrical conductivity. So these trade-off relations make high ZT difficult to achieve. And I personally believe to achieve a really high ZT, we need a new material with different or with thermoelectric behaviors that is qualitatively different from the traditional materials, so that we can, to some extent, we can avoid these trade-off relations to reach high ZT. And in our research, we propose that the topological-insulator nanostructures exhibit unconventional thermoelectric behavior and can reach high ZT. We have written two articles about this. One is about three-dimensional nano-thin film made of three-dimensional topological insulator, and published in the SCS Applied Energy Materials. And the other one is about nanoribbon and made of two-dimensional topological insulator, and published in the Nano Energy. And this is our table of contents figure in our Nano Energy article. In this article, we predict that the two-dimensional topological insulator nanoribbon can have ZT larger than 10. I think ZT larger than 10 is quite a crazy number. Even though this is I think it's a crazy number, but all the three reviewers of Nano Energy gave us positive comments. Means they all agree that our prediction is reasonable. And I hope in the future we can experimentally verify our theory. As an example, we consider a single layered recurring tera, which is a two-dimensional topological insulator. Its topological non-trivial edge state comes from the band inversion around the gamma point. Here is the two-dimensional band structure. Here we can see the direct band gap around the gamma point is quite large, about 300 millivolts. So the decadence of the topological edge state should be quite small. And this is the ribbon structure we considered. The ribbon width we consider is about 14 nanometers. And its two edges are terminated with different structure. The left edge is terminated with a zigzag parallel chain, and the right edge is terminated with the canyon telluride prismatic chain. So here we can see the ribbon band structure. The in-gap topological edge states at different edge at different velocities, and we can see the decadence of the in-gap topological edge state indeed really small, smaller than 3 nanometers, much smaller than the ribbon width. So there is almost no interaction between the topological edge states at different edges. Besides, at the same edge, the topological edge state moves forward and backward, have upside spin polarization. So the backward elastic scattering is also forbidden. As the result, the in-gap topological edge state should have large relation time, much larger than the other states which are outside the bucket. So we call the intact topological edge state the long lifetime state. The other state, the short lifetime state. Now we know that the intact topological edge state should have a large relationship time. The next question is how long it would be. Because of the lack of the experimental data of single layer, the planetary nanoribbon. Let's consider another case, the bismuth selenide thin film, which is the bismuth selenide is the most typical three-dimensional topological insulator. The intact topological surface state of the bismuth selenide film should also have large relation time because its backward scattering is also forbidden, and the topological surface state are localized around surface. It is the measured electrical conductance as function of the film thickness. Here we can see when the film thickness is larger than 6 square layers, the electrical conductance increases linearly with increasing thickness. And if we extrapolate this line to the zero thickness, we find a large. 5 minutes.
Sorry.
We find a large zero thickness conductance, and this zero thickness conductance should comes from the topological surface state. And then we can see when the film thickness is reduced to that smaller than 6 quintal layers, the electrical conductance decreases abruptly. This should be due to the interaction between the topological surface state at different sites. From this measured electrical conductance and the SDH oscillation, which gives us the Fermi wave number, and the band structure from the DFT calculations, and the Boltzmann transport equation, we can conclude that the long lifetime state relation time is about 230 femtoseconds, which is much larger than the short lifetime state relation time, would be about 1 femtosecond. And we can calculate the ZT as a function of Fermi level, and the optimized ZT can be about 2, which is about 10 times larger than the arc value. The intact topological edge state for two-dimensional topological insulator should have the relationship time much larger than the intact topological surface state in three-dimensional topological insulator. This is because for two-dimensional topological insulator, the one-dimensional topological edge state can only move forward or backward. So there is no scattering in between 0 and 180 degrees. While for three-dimensional topological insulator, the two-dimensional topological surface state can move along any directions in a plane. So this allows the scattering in between 0 and 180 degrees. So we set for a single layer of the planetary line, we set the long lifetime saturation time 5 picoseconds, which is about 1 order larger than the value of the bismuth selenide. And the resulting ZT we find can be larger than 10. And in fact, we also calculated the ZT as functions of the long lifetime saturation time. We find even if the long lifetime saturation time is as low as that's comparable with the bismuth selenide, the resulting ZT remains quite large, about 5 at room temperature. So now let's explore the underlying reason why it can have such a high ZT. So let's first see the electrical conductivity and the Seebeck coefficient as functions of Fermi level. We first see the green dashed line. The green dashed line are those only consider the short lifetime state. So they show the behavior of normal semiconductors. While the blue dashed line are those incorporating the in-gate large edge state. So they show the behavior of the topological-insulator nanostructures. Here we can see the topological-insulator nanostructure indeed show behavior qualitatively different from the normal semiconductors. Besides, you can see at the uptimes, the Fermi level, the pure energy here, even though this is in the short lifetime state energy region, the electrical conductivity is quite high and dominated by the long lifetime state. Here we can see the blue lines is the blue is the red line. For the Seebeck coefficient, it shows anomalous behaviors. The Seebeck coefficient is positive for N-type doping and negative for P-type doping, opposites to that of the normal semiconductors. And its magnitude can increase with increasing carrier concentration. This is also opposite behavior to the normal semiconductors. So, to understand this anomalous behavior, let's first note that the Seebeck coefficient is proportional to the energy difference between the Fermi level and the average energy of differential conductivity. For most metals, the average energy of differential conductivity is very close to the Fermi level, leading to a small magnitude of Seebeck coefficient. For degenerate N-type semiconductors, because the density of states increases with increasing energy, the average energy of the differential conductivity will be higher than the Fermi level, leading to a negative Seebeck coefficient. For the topological-insulator nanostructures, the story can be very different. Even though the Fermi level lies above the conduction band edge, because the in-gate electrons are nearly scattering free, the average energy of differential conductivity can be lower than the conduction band edge, leading to a large separation from the Fermi level and hence a large magnitude of Seebeck coefficient with a positive sign. Another phenomenon we predict is the Wiedemann-Fessler violation. Before we discuss the Wiedemann-Fessler violation, let's talk more about the Wiedemann-Fessler. The Wiedemann-Fessler tells us the ratio of electrical conductivity to the electronic thermal conductivity at a given temperature is constant. This means the charge transport and the electronic heat transport are guided by the same scattering mechanism. However, essentially, they should be different. This can be seen from our daily experience. If we put a metal spoon into a hot pot, the whole metal spoon can get hot in a short time. This means the metal can conduct the heat very efficiently. But if we take this metal spoon, we do not get an electric shock. So even though the net charge current is zero, the electron heat current is not necessarily zero. So let's illustrate by this two-level toy model. Even when for the open circuit condition, even though the net charge current is zero, the carrier flow for each level is not zero. For higher energy level, the carrier flow from the hot side to cold side. For the lower energy level, from the cold side to hot side, leading to a net heat current from the hot side to cold side. An important thing is that the amount of the heat provided by each carrier exchange between the hot side and cold side is the energy difference between these two levels. So for a real solid with a quasi-continuous electronic structure, a localized localized conduction electrons will lead to a low electronic thermal conductivity and hence a large ratio of electrical conductivity to the electronic thermal conductivity. This is the fundamental reason why the Wiedemann-Fessler law predicts that the ratio of electrical conductivity to the electronic thermal conductivity is inversely proportional to the temperature. From the Boltzmann transport equation, the ratio of electrical conductivity to the electronic thermal conductivity can be written in a more general form. There is an additional factor, pi squared over 3 delta. Here, the delta is a variance measuring the burden of the differential conductivity along the reduced energy. So a localized differential conductivity will lead to a small variance and the ratio of electrical conductivity to the electrochemical conductivity larger than that's predicted by the Wiedemann-Fetzer law. So let's see the ratio this vector I squared over 3 delta. We call it RE. This is dimensionless. This is the ratio of electrical conductivity to the electrochemical conductivity divided by the value given by the Wiedemann-Fetzer law. For most metals, because the density of state and the realization time around the Fermi level are weakly energy dependent, the differential conductivity will have a shape very similar to the Fermi window function. In this case, the variance is about pi squared over 3, and the variance data is about pi squared over 3, and the RE is nearly equal to unity, and we go back to the Wiedemann-Fetzer law. For the topological-insulator structures, the differential conductivity can become more localized because the in-gap electrons are nearly scattering free. This reduces the variance data and enhances the value of RE. At low temperature, the RE can be about 3 times larger than that's predicted by the Wiedemann-Fetzer law. When the temperature further increases, the reduced gap epsilon G, which is the long-line tested energy region over Eg ribbon over cavity, this reduced gap decreases. This further this makes the differential conductivity more localized and further reduce the variance data and enhance the value of RE. And the reduced gap can be at a given temperature can be reduced by band structure engineering. And we find the long-line tested energy region can be reduced when we apply a uniaxial tensor strength along the x direction, or the both tensor and compressed strength along the linear direction can reduce the long-line tested energy region and the reduced gap. And without, at the same time, we do not significantly change the decadence of the topological edge state. For example, we consider 4% tensor strength along the direction. In this case, the reduced gap is about 0.9. This means the long-line tested energy range is about kT. And the RE can be about 10 times larger than that predicted by the Wiedemann-Fetzer law. Another thing we care about is the optimization of the carrier concentration. So let's see the RE and the seedback coefficient as function of Fermi level for n-type doping. Around the conduction band edge, the RE and the seedback coefficient are nearly equal to their long-line time state part, and increase with increasing Fermi level. When the Fermi level further increases, the long-line time state duration time decreases, and the short-line time state duration time, long-line time state carrier concentration decreases, and the short-line time carrier concentration increases. So both the RE and the seedback coefficient deviate from the long-line time state part, and then decrease. We find that the optimized Fermi level, the PA energy, always lies in the energy region where the RE decreases and the seedback coefficient increases. This means the RE deviates from its long-line tested part at lower energy than the seedback coefficient. We have calculated many cases that they all show the same result. So this is not by accident. There should be a reason behind this. So to understand this, let's first see let me first note that the total electrical conductivity is just the long-line tested part, the sum of long-line tested part and short-line tested part. And the seedback coefficient is a layer weighted average. So for seedback coefficient, when the Fermi level is close to the long-line tested region, the long-line tested conductivity dominates, and the seedback coefficient is nearly equal to its long-line tested part. As long as the short-line tested part, short-line tested conductivity comparable with the long-line tested conductivity, the seedback coefficient will deviate from its long-line tested part. As for the ratio RE, this is the ratio of the electrical conductivity to the electron thermal conductivity. Unlike the electrical conductivity, which is the sum of contributions from each single carrier, the electron thermal conductivity comes from the exchange between two carriers, as we discussed previously. So the electron thermal conductivity can be written in three terms. The kappa LLS is, we call it long-line tested intra-channel exchange term. It comes from the exchange between two long-line tested carriers. And similarly, kappa SLS from the exchange between two short-line tested carriers. And the kappa INT, we call it long-line tested, short-line tested inter-channel exchange term from the exchange between one long-line tested carrier and one short-line state carrier. So around the conduction band edge, the kappa LS dominate, long-line tested part dominate. As long as the interchannel part comparable with the long-line type intrachannel part, the RE deviates from the its long-line part. So this is this interchannel part is the reason why the RE deviates and its long-line tested part is lower energy than the seedback coefficient, because the seedback coefficient do not have such like the long-line tested, short-line tested interchannel part. Now let's see how to improve the ZT by introducing defect. Because the long-line tested topological edge states are localized around the edge, introducing defects in the middle region has almost no effect on the long-line time state. But it could largely reduce the short-line time state registration time. So now let's see what happens when the short-line time state registration time is reduced from the 1 femtosecond, the blue line, to the 0.2 femtosecond, the red lines. Here we can see around the PN energy, both the electrical conductivity and the seedback coefficient are dominated by their long-line time state part, while for the electron thermal conductivity, as we mentioned previously, it has a significant portion of the long-line time state, short-line state interchannel part. This term can be significantly reduced by decreasing the short-line time state registration time. So introducing defects in the middle regions can significantly reduce the lattice the thermal conductivity without noticeably deteriorating the electrical conductivity and the seedback coefficient, leading to the enhancement of RE and ZT. Now let's see the bipolar effect. For normal semiconductors with small gap, the bipolar effect can severely deteriorate the thermoelectric performance by reducing the magnitude of seedback coefficient and by increasing the electronic thermal conductivity. At high temperature, the bipolar effect becomes more serious because of the increase in the minority carriers caused by the thermal excitation. So let's see the result at high temperature, 7 degrees Kelvin. And we notice that our show light, the bipolar effect on the semiconductors can be understood from our short lifetime state result, because the short lifetime state result shows the behavior of normal semiconductors. To examine the bipolar effect, we further decompose the short lifetime state into conduction band state. That is the band above the state above the conduction band edge, and the valence band state, the state below the valence band edge. And the short lifetime state conductivity is just the sum of the conduction band conductivity and the valence band conductivity. And the short lifetime state feedback coefficient is their average. For heavily n-type doping, the Fermi level is much higher than the conduction band edge. The conduction band conductivity dominates, and the short lifetime state feedback coefficient is nearly equal to the conduction band feedback coefficient, which is negative. Similarly, for the heavy hole doping, the short lifetime state feedback coefficient is nearly equal to the valence band feedback coefficient, which is positive. When the gap is small and the Fermi level is less around the gap, the conduction band and the valence band conductivity are comparable. Their contribution, their feedback contribution, can be effectively cancel each other out, causing a small magnitude of feedback coefficient. This is the bipolar effect on the feedback coefficient. For topological insulator nanostructures, the in-gap topological edge states are incorporated. The long lifetime state conductivity can overwhelm the short lifetime state conductivity. So the feedback coefficient is nearly equal to the long lifetime feedback effect. So the bipolar effect does almost no harm to the feedback coefficient. As for the electron thermal conductivity, the bipolar effect comes from the carrier exchange between the conduction band state and the valence band state, as indicated by the light green line here. This term can be significant if the in-gap topological edge states are not incorporated. When the in-gap topological edge states are incorporated, the long lifetime state instructional term or the interchannel term, long lifetime state, short lifetime state interchannel term can overwhelm the bipolar term kappa EH. Here the long lifetime term is the red line, and the kappa interchannel term is light blue line. They can and these two can overwhelm the light green line, the bipolar term. So the bipolar effect also does almost no harm to the electronic thermal conductivity. As a result, the topological insulator nanostructure can be exempted from the bipolar effect. Yeah, this is my summary. We demonstrate that the topological insulator nanostructures can show conventional thermological behavior due to the dramatic difference in the scattering intensity between the in-gap topological edge state and the bulk state. And the feedback coefficient shows anomalous behaviors with large magnitude. Here the anomalous behavior are the upside sum to the normal semiconductors, and it can increase. Its magnitude can increase with increasing carrier concentration. And the Wiedemann pencil can be violated with the several times enhancements of the ratio R or the ratio of electrical conductivity to the electronic thermal conductivity. Introducing defects in the middle bulk region can reduce the thermal conductivity without noticeably deteriorating the electrical conductivity and the feedback coefficient, leading to a further enhancement of RE and the ZT. And the topological insulator nanostructure can be exempted from the degradation caused by the bipolar effect, even if the bulk gap is small and the temperature is high. Because of these unconventional thermological behaviors, our calculations demonstrate that the ZT larger than 10 is highly likely for a single layer, the planetary Nanoribbon. This is my report. Thanks for your attention.
Thank you very much. Hello, I'm Shaggy. You have mentioned that you reach ZT up to 10. So have you included the latest thermal conductivity calculations in these?
Yeah. We have calculated the latest thermal conductivity, also based on the first principle. But not maybe not so as we focus here. Yeah.
Thank you.
Sorry, I have a question about how you distinguish the short lifetime state and long lifetime state. I don't understand. Sorry.
The short lifetime states are the states in the put here in the bucket. Yeah, in the bucket. The in-depth larger edge state has a relation much larger than the other states outside the bucket.
Oh, so the outside the bucket, and it is a short life state.
Yeah.
Sorry, I also a question about you say you introduce defect into and affect your conduction, but what defect you introduce? Is vacancy or interstitial side or?
I think we can introduce here. We do not specifically consider what defects we induce, but if we introduce defects in the middle region, it will not affect the long lifetime state. So the long lifetime relation will not affect, but the short lifetime state should be can be reduced because the short lifetime state wave function can be a large portion in the middle region. Yeah.
Okay. Thank you.
Any more questions coming? I got one naive questions. Well, from the side view of your structures, it looks like these kind of 2D layers could be easy to buckle or corrugated. So have you calculated stability of these 2D structures?
Stability, we have calculated but we calculate film, not river.
Right.
Film structure, and the film structure, the photon dispersion we have calculated.
Right, but not the ribbon.
Yeah,
Not for
river.
ribbon.
Not for river. Yeah.
Okay. Right, thank you. More questions? Okay. If there are no questions, then thanks for Professor Wang again, and thanks all the speakers in the afternoon. I think I passed the